Okay, good morning. So we'll have the third lecture and last lecture from Dr. John Paley. So as the students are coming, we should just let's get it started. But however, I wanted to tell the Slack. I do not see any response to John's questions. I do not see any questions also. So, the school has, we have gone through a lot of effort to make it useful for you. So it is very important that he has a talks also uploaded there. So I would really request you to go over the slides, answer his questions as well as put some questions. If you don't put any questions, basically you have not gone through slides and you have no query. So just please go through. I will just repeat when all the students are around, but please put some questions, okay? With that, I am just, John, over to you. Thank you.
Okay, let's see, can you hear me okay?
Yeah, you can make the full screen mode, yeah.
Yep. Okay. All right, well, welcome back everybody to my last lecture on neutrino scattering. And so today I'm going to be talking about what we know and what we don't know. And mostly I'm going to be giving a review of the experimental side of of the types of measurements that we have and some of the issues that we see. Okay, so again, a reminder that I might have some questions in my slides that I'd like you to please consider. But more importantly, I think it would be great if you would send me at least one question after each lecture. So of the previous two, I don't think I've received any questions yet. So I'm here for you. And I'm happy to talk to you about anything really, but especially this topic. So yeah, please don't be shy. Okay, and yeah, you can send me questions via email or Slack. Okay, so today I will give a brief review of some of the experiments that I'll be talking about and how they work and some of their capabilities. And then I'll get into the measurements. And so we have a whole bunch of different measurements. We have the masonless or the 0 pi measurements and something kind of related to that, which is what I like to call the 2p2h saga. Then we'll explore the kind of a unique way to see the impact of final state interactions and measure the impact. Then I'll talk a little bit about pion production and then inclusive measurements and then electron neutrino measurements. And then finally, I'll wrap it up with a couple slides on what we need with all of this massive amount of information, what we need to do, and a look to the future. Okay, so as a reminder, as I discussed yesterday, we develop models for neutrino scattering depending on their modes, right? So we have the charge current quasi-elastic interaction, the resonant interaction, 2p2h, SIS and DIS. These are all what we call interaction modes. But in an experiment, we don't see those modes. We only see what comes out of the nucleus. Well, hopefully that's what we see. And so we classify experimentally, we can really only measure what we see. And so we classify our measurements according to their topology, right? So if we see no pions in the final state, we call that CC0 pi. If there's only one pi or one pion, then we call it CC1 pi. Maybe we go with a 0 pi, but maybe one or more protons. these are the different topologies, right? So, and there is a close correspondence to the interaction modes, but there's some mixing in between them. All right. So, the types of interactions that I'm going to talk about today that we're measuring in our experiments are done by topology. Now, the other thing is that the experiments making these cross-section measurements have different sensitivities, meaning they have different levels of all of these topologies, right? So if you think about the T Decay experiment and the SBN experiment, their flux is basically mostly below 1 GeV at lower energies, right? So, and if you look at the cross-section as a function of energy, at low energies, you're basically dominated by quasi-elastics, right? So most of the measurements coming out of here, the most powerful measurements that they can provide are on the 0 pi, right, which are mostly the quasi-elastic and 2p2h with a little bit of feed down from the resonance. Whereas on the opposite end, we have Nova and Minerva at a few GeV, peaking around a few GeV, and those now have actually a very significant number of resonant interactions, still a very large number of quasi-elastic, but also some DIS. So they have a real mix of all of these different topologies, which makes it both fun and interesting, but also a challenge because if you want to try to measure one topology, then these other ones are these other types of interactions can be a bit of your background and make kind of interpreting the results a little bit trickier. Okay, so now I want to talk about the experiments and their detectors. So first, I'm going to start with Minerva. Minerva is an experiment at Fermilab. It sat in the NUMI beam on axis, and basically it's a fixed target experiment. Well, all of these experiments are fixed target experiments, but it consists of a central region called the active tracker region. These are made of plastic scintillator of this shape here, of this triangular shape, which give excellent spatial resolution of about 3 millimeters and excellent timing resolution of about 3 nanoseconds. And so in the NUMI beam, we actually have a very high rate of neutrino interactions. So you need this timing resolution so you can separate out all of the neutrino interactions that occur in the 10 microsecond spill. And so in the active tracker region, so this is again mostly plastic scintillator, so it's mostly a hydrocarbon CH, and that's surrounded by on the sides there's an electromagnetic calorimeter and a hadron calorimeter, and so the beam is coming in from the left. So they have a steel shield and a scintillator veto wall there. They also had some liquid helium here, but I think for most of their running, this was empty, and they did not take data with the with helium. They have some data, I believe, with helium. And then upstream of the tracker, they have a bunch of different nuclear targets of carbon, which I believe is graphite, and then lead, iron, and water. So you can see the length of this is about 5 meters, so it's a decent size detector here. Now, here's what the data look like. This is an event display from Minerva, where the beam is coming in from the left, and a neutrino comes in. We don't see anything, and then it interacts here and produces a muon and a proton track coming out. And so these are kind of straight lines, right? And so they perform reconstruction and they form particle trajectories, which we often refer to those as tracks. So a muon track and a proton track here. The particle ID is done mostly via DEDX in this active tracker region. But it also has limited angular acceptance because the way it measures the energy of the muon is that downstream of this whole thing here is the Minos near detector, right? And the Minos near detector is mostly an iron calorimeter with also with scintillator tiles or scintillator and uh, and so sorry, and it was also magnetized, right? So if a muon enters the Minos near detector, it would bend. You could match up the trajectory with the trajectory in the Minerva, and from the bend you can get the momentum of the muon. Nevertheless, the Minos detector is all the way down here, and so if a muon went out the side, then it can't measure it, right? So it has a finite or it has a limited angular acceptance for the especially for the muons. And again, there's a variety of nuclear targets upstream here. That enable cross-section measurements with different nuclear targets, meaning you can see how the cross-section depends as a function of the atomic number. Then next door, literally next door to Minerva is the NOVA near detector. So NOVA, the near and far, NOVA is an oscillation experiment, so it has two detectors. It has a near and a far. This is the near detector. Both detectors are functionally identical. The near detector is 300 tons of it's this PVC material here filled with liquid scintillator. And then inside these cells, there's a wavelength shifting fiber in here that captures the light, the scintillation light, as charged particles go through. They produce light, bounce off the walls, captured in the fiber, and then it's routed to an avalanche photodiode here, where we record the time and the energy, and of course the channel, which tells us where it hit. So this detector is kind of a light Z calorimeter, meaning that basically an electromagnetic shower will form, and we can see the shape of it by the mere fact that each one of these cells is only a fraction of an interaction length. And so these cells and the size of them and everything else was designed so that we could optimize electromagnetic showers, or the identification and measuring the energy of electromagnetic showers. Now the material here is a mix of stuff. So this is PVC. So that means that it's hydrocarbons, but also there's some chlorine and there's some titanium dioxide, which is the white, basically the whiteness of the PVC of the plastic here. We had to make it very white so that the light would, the scintillation light would reflect off the walls, bounce off the walls until it was captured in the fiber with minimal loss from the reflections. But it is mostly a hydrocarbon detector, carbon and H2, but there are some heavier elements here that make it a bit unique. So here's what interactions look like in the NOVA near detector. You can see this is actual data, and so you can see the neutrinos coming in and interacting in the detector. And this is, for example, this is a candidate where with a with a muon and perhaps a proton or a pion here coming out of the vertex. This is another neutrino interaction, as is this one here. This one, though, it looks like it is uncontained, meaning that this is a side view and this is a top view here, that this is going out of the coming out the bottom of the detector. Now, at the end of the near detector, there is what we call the muon catcher. This is made of a combination of steel and the NOVA cells. And it's designed, it has enough steel and material to range out 2 GeV muons that come from vertices upstream. So if a 2 GeV muon is created here, then it will be stopped in the muon catcher, right? Kind of like, see how this green trajectory here, that's a muon coming in, and it stops inside the muon catcher. We also have a very good timing resolution in this detector. It's a fast detector. It's 5 nanoseconds. Hit level timing resolution that we use to separate. Again, that we have many neutrino interactions per 10 microseconds spill of neutrinos coming from the accelerator. So the different interaction types are shown here, or just a couple of examples of them. So primarily what we're worried about in NOVA is measuring charge current nu mu interactions and nu e interactions. The nu mu are kind of characterized by a long straight track, which is the muon. For a nu e, an electron comes out and creates an electromagnetic shower. And so this is characterized by a shorter, wider, kind of fuzzier trajectory, and that's actually it's a shower, and so that's what a nu e's charge current interaction can look like. And then finally, we have neutral current interactions where there is no lepton in the final, no charged lepton in the final state. The muon is in the final state, goes off on its merry way, and we don't see it. But we can see some of the other particles that the neutrino can produce, right? And so it could be a pion or a charged pion, or a pi zero, or a proton or a neutron. So NOVA is an oscillation experiment, and so the detectors in the reconstruction are designed to optimize muon identification and muon measurements, as well as electromagnetic shower measurements. So NOVA is very good at identifying and measuring the energies of muons, electrons, and pi zeros in the final state, and we're working on improving the reconstruction of all of the other particles. Okay, then there's T-decay in Japan, and again, this is also an oscillation experiment. However, they have a very sophisticated near detector, because their FAR detector is a water Cherenkov detector, and so they really need their near detector to put some heavy constraints on all of both the flux and the neutrino cross sections that they have to worry about in the experiment. So this detector consists of time projection chambers shown in here, these orange blocks here, and then fine grain detectors, which are made out of plastic scintillator. And so these are also tracking detectors as well. And so this is primarily their target for neutrino interactions. The TPCs are gas, and so you don't get many interactions there to begin with. But it's also mostly, these are mostly argon gas in here, which is a much heavier element. Whereas carbon is, well, it's different from oxygen, obviously, but maybe not too different. And then, so this one also contains some water in here. So they use the TPCs for particle ID, and they can also measure. Sorry, this whole thing sits in a magnet. This is the old UA1 magnet that they got from CERN, and so the charged particles will bend. They'll bend a lot in the gas, and maybe just a little bit in the plastic, but they use the bend here to measure the momenta of their particles. And then coming back to Fermilab, we have microboon, which is part of the short baseline neutrino program. And so the short baseline neutrino program consists of 3 liquid argon TPC detectors. Liquid argon TPC. So the microboon is about the size of a school bus. So it's I believe it's 35 tons of liquid argon. So it's not the biggest, but it so far it's the experiment that has the most data. There are other liquid argon TPCs that are just turning on now or being commissioned. And so and those are actually much larger, and there's another large TPC which will serve as a near detector, which will be exposed to a very, very high rate of neutrino interactions and will collect enormous statistics of neutrinos interacting on argon. So the way a liquid argon TPC works is that a charged particle traverses through the liquid argon, it ionizes the liquid, and then a strong magnetic field pulls the electrons through the liquid and onto a readout plane. In this case, because these are rather large detectors, the readout planes are made out of wires instead of say individual paths. That keeps the channel count down and the cost down. And so you have a signal recorded on these wires, and you can see the signal shown here in the red and the blue. Here's what an event or a couple of event displays look like in microboon. So again, the classical signal of a neutrino interaction is nothing, and then suddenly a whole bunch of particles coming spewing out. And so you can see the amazingly fine detail that we can get from liquid argon TPCs, or really just TPCs in general, when you have them pixelated, or you have the channels small enough in size. And so these are very, very high detailed photographs of neutrino interactions that you can see the individual particles coming out. You can see electromagnetic showers, etc. So they're really, there's just a huge amount of information coming out of these detectors. And by having such detail available to you, you can push down to very, very low detection thresholds, and actually like reconstruct trajectories of particles with tens of MeV of energy, which you can't do with any of the other detectors that I talked about earlier. Okay, so those are the detectors. So now I want to get into a brief summary of some of the measurements and their comparisons to event generator predictions. So I'm just going to preface this that I don't think you're going to be like wowed by by the plots, because the news is not so great. In general, the generator predictions are pretty far off from our measurements. Not orders of magnitude, but definitely you'll see kind of repeated over and over again that there are significant discrepancies between what we see in our data and what our neutrino event generators are predicting. Now, also, I just want to note that this is a really huge topic, right? Neutrino cross sections is a really big topic. And there's no way that I can cover everything in this one lecture. So I have some suggestions if you're interested in learning more. If you want to check out or get involved in NewSTEC, NewSTEC is the Neutrino Scattering Theory Experiment Collaboration. So it's an international collaboration of neutrino scientists, both theorists, experimentalists, and people who work on neutrino event generators. And we all get together and try to solve the mysteries of neutrinos, in particular of neutrino interactions. We also have a NewSTEC, that's supposed to say NewSTEC News email list, and so people occasionally post here. And that's a useful thing that we have set up. So you can go to that website for instructions. There's also a white paper that is a very nice summary of kind of where things stand with neutrino interactions. Now, this was written in 2017. There have been many new measurements since then, and definitely some improvements with our modeling. So the white paper covers both measurements and the theory and the predictions. Um, and it gives a very nice summary of what the major issues are that we are considering. And then we have a new white paper coming out, hopefully later this year, from NewStack, and this will be kind of a bit of an updated version from the one we published in 2017. And the idea here is to kind of update it with what we've learned since then. And then finally, we just had the New Int workshop, which is held every 18 months. And so if you're interested in seeing more, learning more, take a look at the talks. They are publicly accessible for this workshop, and the link is here. Okay. So I want to start out by talking about the 2P2H saga, because this is something that has been around for a while and still hasn't been resolved. So in 2016, Minerva published results showing a measured cross-section that was much larger than was predicted in their event generator at low momentum transfer, right? So you can see at the top plot here that there is that the measured cross section is much higher here than what the generator prediction was saying, and it happens that the excess here, that the larger cross section is happening at momenta transfer that is consistent with 2P2H interactions. Now, 2P2H interactions, this was a process that was already known from electron scattering experiments. And so this had been known for years, and in fact, around this time, people had started to implement models for 2P2H into the event generators. But then when we made our measurements and compared our data to the predictions, it was clear that the 2P2H models just weren't strong enough or didn't fully explain this excess here. And then shortly thereafter, Nova showed a similar discrepancy in their data, and so that's shown here, where the prediction is either in the red or the dashed line for two different 2P2H models. But even there's a large discrepancy here, and that is also shown here as an actual cross-section measurement here. And as it turns out, both Minerva and Nova, we've tried different models to see if they can explain if any of the models can get close to it. And it turns out that there's actually no theory model that's really able to fill in the gap that we see here in the data. And yet, if we look at the lower momenta, if we look at microboon and T decay, it actually seems that that their generator predictions that are the community's generator predictions don't do too bad of a job. Now that may appear odd to say, considering that this is much lower here. But when you look at it quantitatively and you calculate the chi-squared using the full covariance matrix of the measurement here, it turns out that you actually get a pretty acceptable chi-squared for these, and it's most likely due because the shape of this is rather consistent with this, right? So it's basically you're just missing some normalization constant for component here. So that's I find this strange personally, and no one can really understand why this looks fairly reasonable at lower fluxes or lower energy fluxes, like for T decay and SBN. But then when you get to higher energies of a few GeV or higher, then it really kind of just it gets pretty muddy, and it doesn't look nearly as good. So either there's an unaccounted neutrino energy dependence in 2B2H interactions. I've seen some ad hoc energy dependence added in, but they're not really well motivated. Well, they're not at all motivated by theory. And so there hasn't been a theory that I've seen that shows an energy dependence that could explain what we're seeing here. So it's either that, or maybe there's something else that we're just not modeling at higher energies, that somehow the higher energy experiments are sensitive to, whereas the lower energy are not. And this is a conundrum, and it's been going on since the mid teens, ever since Minerva published this result. And there's a lot of theory work going into try to understand what's happening here, but so far we're kind of drawing a blank. So this is a major issue that we as a community are working on. Okay, now I want to get into the other specific measurements. So we're going to talk first about 0 pi measurements. So as a reminder, 0 pi are the kind of like the quasi-elastic measurements. So the T decay measurements. So this is for again for a charge current interaction. When I say charge current, in almost all of these, unless I say explicitly that they are electron neutrino, they are either muon neutrino or anti-muon neutrino measurements. And so this is a double differential measurement here for 0 pi. And you can see that the data and generators have a so-so agreement. It's not really great, especially for the momentum dependence of the muon. But then if you look at Nova and Minerva at higher energies, where they've done done some analyses where you are able to kind of isolate a sample that is more has more quasi-elastic and 2p2h interactions in them. And then if you compare the measurement to the different predictions that are out there, you can see there's a first of all the generators, there's a very broad range of predictions here, but in general there's really no good agreement between the data and the generators. Now both Minerva and Nova have something called a tune. This is where they have done some adjustment of their neutrino scattering model. And these are typically based on external information from other experiments. In the case of Nova for 2B2H, Nova uses its own data to kind of fill in the gap, so to speak, for the 2B2H events. And so if you look at these plots and you might say, oh well, this kind of brick red color here or whatever looks like it's within the error band for the most part. Well, that's because it is by more or less by design. Not re, so Nova did not use these same observables to tune its simulation. It used different variables, which is why you don't see perfect agreement here in this curve here, right? This is the Nova tune. So there isn't perfect agreement, but it's in general flatter than all of the others. For Minerva, this is so this plot shows comparison to their tune, only to their tune, but they've included the components of the different interaction modes to their tune, so you can kind of see how some of these might play a role in the shape, right? So like this one here, okay, it falls down kind of like this one here, but then it comes back up. And that's where these two methods these two interaction modes kind of meet in here and and then um, and then come back up. And so you can kind of see where maybe that you need some extra strength for either quasi-elastic or 2p2h, that kind of thing. But in general, even after they've tuned their simulation, you can see that there are rather large discrepancies between their tuned simulation and what they see in data. All right, now another really unique thing that has come about in recent years is the use of transverse kinematic imbalance to probe final state interactions. The transverse kinematic imbalance is basically so if you think about the neutrino coming in and interacting, then the plane that is normal to the direction of the neutrino, you can define the transverse momenta for the final state particles, right? So this is for the final state lepton. This is the transverse component of it, and then for the nucleon, this is the transverse component of the nucleon momentum. And so you can draw a bunch of angles between all of these things here, but effectively what you're looking for is missing momentum in the transverse plane, which is just something that shouldn't happen. Okay. Now, if you then look at how FSI, the final state interactions that occur inside the nucleus, right? If you look at how those affect the distributions of things like the missing momentum angle, etc. If you take the ratio of the prediction with FSI and without FSI, then you can see that there are really huge effects, right? With FSI, the phi 3D, one of the angles here is increased by more than a factor of 5, which is just that's a huge effect. It should really stick out, at least according to Neuro. And then there are a couple. Oh, excuse me. It is late here. Sorry. The generator predictions show, though, that they're all fairly sensitive to this. Similarly, you can see that there's with FSI, you tend to suppress the missing momentum angle at lower angles, right? And so it goes down here. And then it goes above 1 here, so they're kind of pushed a bit to larger angles. Right? Mike Brune has done some analyses where it's looked at these kinematic imbalance variables, and And you can see the results here, right, with compared to different generators. So here are some measurements, and here are some generator predictions. Again, they're overall the shape is pretty reasonable here compared to what we see in other distributions. The shape is not bad at all. And so in here for this distribution for Phi3D, you can see that most of the generators do actually a decent job getting the shape of that right. But if you look now at PN, this is a region where I believe this is where you have more resonant interactions occurring, and this is a region where you're going to have more FSI effects. And Jibu has kind of the best FSI model out there because it's very well theoretically motivated, the FSI model, and implemented from a theoretical basis. And so it's kind of not, I think, terribly surprising that Jibu has a pretty good agreement here compared to the other generators in this region where FSI is important. All right, so at NewInt, Stephen Dolan talked a bit about some of the measurements, the 0 pi measurements they've done in TDK. And in TDK, they're able to measure both the muon and the proton kinematics. And so when you do that again, you can look at this kinematic imbalance. And in general, it looks like it does okay. But there are some things that they learned by doing this. So first of all, it's clear that no model is perfect. But on the other hand, the error bars on these data points are also quite large. So I don't know how much we can read into that. Then the RFG, which is this dashed line down here, right, is rejected by the data and rejected pretty strongly. And then let's see, yeah, and then some other things. So what they want to do is they want to figure out in this sample, the 0 pi sample, what fraction are quasi-elastic versus not quasi-elastic, right? If they're not quasi-elastic, then they're probably 2p, 2h. And you need to know this relative fraction pretty well because they need to use that in making sense of their FAR detector data where they can't actually see the proton in the final state. And so they have to, for a certain fraction of events, they have to, kind of put this effect in there. Yeah, well, we can move on. All right, so then Minerva has also been looking at transverse kinematic imbalance. And here they're looking at now even more of a breakdown of the transverse momentum in the Y direction and the X direction. Just as a side note, I mean, this is something that is one of the beauties of having a huge amount of data is that you can start binning things in interesting ways without losing too much sensitivity because you have so many statistics, right? So you can kind of slice and dice your data up in many different ways. Now, so what they see here is that the tuned cross-section, and again, this is tuned to their own data, but not using these particular observables. But the red curve is their tune. And you can see that kind of in the mid-range of angles, sorry, not angles, of energy, of momenta, sorry, that that their tune does pretty well, right? It actually is pretty much on top of the data. So that looks pretty decent. But then as you go to lower energy and higher energy, then things kind of start to fall apart, right? Then their tune no longer really works for them. So. And then they're also, oh, sorry, so that's 0 pi. Now moving on to 1 pi. Uh, um, so Minerva has measurements here of, now these are single pion measurements. And what we see here is that the angular distribution of pions seems to be relatively well modeled in Minerva. But the energy distribution is peaked at lower energies than most of the models, right? There's also a bit of an excess here, right? Or meaning that the integrated cross section for this process is a bit higher than what the generators predict. Going back to T decay, they also made measurements of 1 pi, and you can see them here. There's pretty reasonable agreement, especially with Newt, which is their generator, whereas Genie, the Genie cross section seems first of all, it seems a bit high, and it also predicts higher momenta and larger angles than the data. Now, so that's for single pion, but we also want to look at n pi, where now n is maybe greater than 1, because as we go to higher energies, the shallow and deep inelastic scattering can produce more than 1 pion in the final state, right? So we know they're there. And then what's important is that for Nova and Dune, most interactions in these experiments involve pion production. So this is particularly true for Dune. I believe it's something like 60% of all neutrino interactions are in the range of being able to produce multiple pions in the final state. And Nova, it's I think nearly 50% or something like that. Now the energy, the reason we care about this is that the energy to create the pion needs to be accounted for when reconstructing the neutrino energy, and this is important for oscillation measurements. So that we want to know how frequently we're producing pions that maybe we don't see, but we have to account for. And also pions are rather susceptible to FSI, and so you can see the effect of FSI on the pion kinematic distribution that we measure. All right, so looking at n-pi measurements, this is for greater than or equal to 1 pi and Minerva. So you can see that there's a whole bunch of different processes that can result with a pion in the final state. And if you add them all up together, then we have some regions of phase space here where our generator is under predicting the number of events, meaning the cross section is too small in the generators. But also the shape looks like it needs some improvement here as a function of energy. And then you can also look at using the simulation. You can now look at the transition from the resonance region into the SIS and DIS when you're looking at these events. And you can see that there's an excess at low PT and high PT, whereas kind of in the mid-range, the intermediate values for PT show better agreement with the base model. So we probably have the peak of the distributions right, but maybe the tail's not quite right. Okay, now moving on to inclusive measurements. So Nova has a couple inclusive measurements. A few years ago, we showed results for the neutrino charge current inclusive measurement here, and so the data are shown in black, and the predictions are shown here, and you can see again there's a wide range of of predictions here. We also are working on publishing another result here, which is the now the anti-neutrino. This is a triple differential cross-section measurement. You know, if we so it's triple differential. Two of the dimensions are in the muon kinematics, but the third dimension is in this E of Veil energy. And the E of Veil is you can think of it as the amount of energy that is related to all of the things you can actually see in your detector, ignoring the lepton, right? So this is all in the hadronic system. So like in NOVA, it would be the scintillation light from protons, from kaons, from pions, but it's important to note that it ignores the energy associated with neutrons. Okay. So anyway, so if you now look at different regions of E of Veil, what you can do now is you become a bit more sensitive to you have a higher fraction of certain types of interactions. So our simulation predicts that we have about 35% of our interactions are mech events, or rather 2p2h at the very low values of E of Veil, and the rest are quasi-elastic, right? So these are kind of the 0 pi in here, right? And what we see, obviously, is that none of the theory-based models fully reproduce our measurements, and the SUSE V2 model better reproduces data than the Valencia. Sorry, the Valencia quasi-elastic model, which I'm trying to point that out here. So that's the purple line and the brown line compared to the blue, green, and red here. Okay. And then for 2p2h it seems like Valencia and SUSE V2 are very similar, and neither model really matches the data though. So, and then if we now move up into higher ranges of E of Veil, now we're getting more resonant interactions in here. So about half of the data are expected to be coming from resonant interactions. And what we can see in this range is that SUSE V2 better describes the quasi-elastic physics, and both theory models, though, poorly describe the 2p2h. So the differences, sorry, going up to even higher momenta, we see that now we're basically dealing with mostly resonant and DIS interactions, and this is where some tuning has been done to the Gini simulation, and the different tunes do different things, but the 211A and B tunes adjust the model to match the external single nucleon data in the modeling res event. And what we find is that the tunes to the external data, that they do perform better than without having any tuning at all in this resonant region. So that's good to see, right? These are the difference there is let's see, I got lost here. Right, these different tunes here. So if you compare the blue and the green to the pink, which is all the way up here, right? This tends to do a bit better here. It's still not perfect, right? It still has a slope here, but it does better than no tune at all. All right, and then Minerva also has again a huge data set that they can slice and dice, and They also took data in two different beam configuration modes, one where the beam neutrino energy is 3.5 GeV and the other one is 6 GeV. Excuse me. Again, the general theme still sticks, which is really no one does a great job of agreeing with the data. All right, and then finally, I want to talk about neutrino electron measurements. So these are important, especially for oscillation measurements or oscillation experiments, because we need to understand effectively what we need to understand is the ratio between or any differences between the muon neutrino and the electron neutrino when it comes to the scattering and the cross section. Lepton universality may be true, but there are other nuclear effects that we have to take into account. There's phase space corrections, there's radiative corrections, and then there's different nuclear effects seen by the muon and the electron. And so ideally what we want to do is we want to measure cross sections for electron neutrinos and compare them to those of the muon neutrinos. But this is a really hard problem to do because we did such a good job creating our neutrino beams that they're very pure beams, and in the ranges of energies that we are most interested in for oscillation measurements, the electron neutrino contamination of the beam is really, really small. It's about 1%, right? So there are very few electron neutrinos in the beam itself. So now you have to kind of go through and identify a very small signal with an enormous background of mu-mu-c interactions. Nevertheless, we persevere, and we are able to identify electrons in the final state. So this is a result from Minerva from 2016 that shows the measured electron. The measured cross section, single differential cross section, is a function of electron energy and electron angle theta compared to the simulation, and there's actually pretty reasonable agreement here, even though the error bars are a bit on the larger side. Nova also made a measurement of electron neutrino scattering. In fact, made the first double differential measurement. And so here you can see things as a function of energy and angle. For the most part, the generators do an okay job. But in the most foregoing region here, you can see at higher electron energies, you can start seeing differences between the different generators, and they're getting further and further apart, further and further away from the data. But again, what we really care about is the ratio of the cross sections for these two. And our current uncertainty on this is about 3%. So measuring this ratio to better than 3% in the current generation of experiments is probably unlikely, but we're working on it anyway. We want to make this measurement anyway, and hopefully in the next year or two you'll see some results on this. But again, in an ideal scenario, we'd be able to nail this cross section down to percent level or smaller. All right, so just a quick summary of the measurements. So overall, most generators seem to do an okay job when predicting the muon kinematics. When measuring the pions directly, the predictions seem to be doing not too bad. but inclusive cross-section measurements seem to imply that pion production is perhaps under-predicted at higher muon energies. So that's a bit strange. And then there is something going on either with 2p2H itself or some other interaction that produces an enhancement of available energy at low momentum transfer. But excuse me, but only for the higher energy experiments. So that's this is the conundrum that we're kind of stuck with. So we have all of this to consider, and the real question is, how do we make sense of all of this? So we don't have an answer yet of how to make sense of all of this. We're still working on it. But many of the generator developers are implementing some kind of global fit of their models to the data. That also, for most of them now, they're also comparing to electron scattering data too, right? The electron and the neutrino are quite similar, and just one happens to carry an axial current. But the vector component is something that we can nail down by looking at electron scattering data. Yeah, but unfortunately, I don't have too much time to get into that. Now, when they're doing these comparisons and these fits to all of these data, it's a lot easier to pull out a specific model for an exclusive final state from a generator, and then in the generator itself, and then if we have a measurement that is very similar, then it just makes it a lot easier to kind of tune and tweak if there are any free parameters in the model using exclusive final state measurements. But there are other tools that can kind of look at things more broadly. So Genie uses the Professor tool, which is also used by JNAD4. Nuisance is another great tool for comparing different data sets to different generator predictions. But no matter what, this is an enormously challenging task, and we're really only just getting started. All right, so I just want to wrap things up. So there's a lot that I did not talk about. There are neutron measurements by Minerva and Annie and others. There's measurements of interactions in the SIS-DIS regime by Minerva, and maybe someday Nova will too. There's using electron scattering data to constrain the vector components of our models, and that's being pursued by the E4NU collaboration. And it's also being done in electron scattering by adding electron scattering into neutrino generators. Hadron scattering measurements to improve our understanding of things like FSI, secondary interactions in our detector media itself. And also, of course, as I mentioned the other day, reducing flux uncertainties, right? So there's a huge amount of supportive experiments going on that will have something to say about some of the nuanced details of our cross sections. And then there's lots of interesting topics considering BSM and NSI and light dark matter when it comes to looking at things in cross sections. The near detector for T decay is being upgraded, so that's very exciting. And they'll have a much more capable near detector, which will be able to provide some even higher quality measurements. And then coming on soon at Fermilab, we have the Dune 2x2 prototype for Dune. This is going into the NUMMI beam, and so it will be exposed to rather high energy neutrinos. And we'll see if anything interesting comes out of that. SBND is the near detector for the SBN program, and it will see hundreds of millions of neutrino interactions that it will, again, be able to slice and dice and do all sorts of interesting things with. Furthermore, all of the experiments that I mentioned today, we're still continuing to analyze and improve upon existing measurements, so there's a lot more to come. So, as we saw from the data, we have our work cut out for us to make sense of it all, but the future is bright, and we need smart people like you to help us, so come join the fun. Thank you.
Thank you, John. So it's almost midnight for him. So can we have one or two questions? One question quickly. Yeah. Okay.
Hello. Hi. Can you hear me?
Yep.
Hi. So I wanted to ask that regarding the flux uncertainties. So mainly the uncertainties are due to issues with our modeling of beamline and other stuff, and we are like trying to then estimate the flux from the near detector, but mainly using neutrino nucleus interactions, because the neutrino electron cross section is small, but still like the neutrino electron scattering will be a cleaner signal, and the flux we will measure from those scattering is good. So can't that be used to reduce some of the uncertainties we have from beam, mainly like hadron production cross sections uncertainties or things like that?
Yeah, no, so yes, so in fact that is the plan, and Minerva has already done this. So they reduced their uncertainty by I believe at least a factor of 2. They reduced their flux uncertainty by a factor of 2 by measuring the rate of neutrino electron scattering in their detector. So it's easier to make that measurement at higher energies, because the way you identify the signal is by looking at very forward-going electrons. As you get to lower energy, the electrons are no longer as forward-going, and then it becomes very difficult to isolate those events from just a charged current, nu charged current interaction. But it's easier to do at higher energies. So experiments like Minerva, Nova, and Dune can do this and are doing it. Nova is working on its analysis now. We'll see. Hopefully soon we'll get some results that we can show everybody. And Dune is certainly planning this as part of the near detector program, is to measure the neutrino electron. So in fact, I think Minerva did use another method. It's called the low Y method, to constrain the flux uncertainties. But there's a lot of skepticism about that approach because it is fairly model dependent. And that is probably something we want to avoid.
Okay, let's thank John again. So thank you, John, for staying awake till midnight. And with that, I'm again requesting students to go back to the Slack page and put the question. There's supposed to be one question from each student per lecture. So if you have not gone back, there is a lecture already, the slides are there. Please go back and put your questions, okay? Thank you, John. Thank you.
Okay, thanks everybody. Enjoy the rest of the school.